बिस्मिल्लाहिर्रहमानिर्रहीम। आज हम चैप्टर 2 का लेक्चर नंबर 3 पढ़ेंगे। जिस तरह हमने पहले लेक्चर में एम्पलीट्यूड मॉड्यूलेशन के चंद पैरामीटर्स और इसके जो है मेरिट्स और डीमेरिट्स, ओवर मॉड्यूलेशन, डिस्टॉर्शन, अंडर मॉड्यूलेशन और इन चीज़ों के हवाले से बात की थी, आज हम टॉपिक 2.3 में साइड बैंड्स एंड द फ्रीक्वेंसी डोमेन के हवाले से बात करेंगे। साइड बैंड or side frequency or side bands are generated as part of the modulation process and occurs in the frequency spectrum directly above and below the carrier frequency। यानी जो साइड फ्रीक्वेंसीज है या साइड बैंड्स है वो कैरियर फ्रीक्वेंसी जो हमारे पास सेंटर में अकर करती है उसकी एक साइड और दूसरी साइड पे अकर करती है, और इसको हम कहते हैं डायरेक्टली अबव एंड डायरेक्टली बिलो द कैरियर फ्रीक्वेंसी। जो फ्रीक्वेंसी कैरियर फ्रीक्वेंसी से कम होंगे उसको हम बिलो कैरियर फ्रीक्वेंसी, और जो हमारे पास ज़्यादा होंगी कैरियर फ्रीक्वेंसी से उसको हम अबव द कैरियर। तो ये दोनों साइड पे हमारे पास साइड बैंड की फ्रीक्वेंसी जनरेट होती है, तो उसको हम कहते हैं साइड बैंड्स एंड द फ्रीक्वेंसी डोमेन। Okay, how to calculate the sideband? So the calculation method of sideband. Single frequency sine wave modulation generates two sideband. यानी अगर हमारे पास सिंगल फ्रीक्वेंसी साइन वेव मॉड्यूलेशन टेक्निक्स हो तो उसमें दो साइड बैंड फ्रीक्वेंसी बनती है। कम्प्लेक्स वेव फॉर एग्जांपल यानी वॉइस और वीडियो मॉड्यूलेशन जनरेट रेंज ऑफ साइड बैंड्स। अगर कोई साइनोसाइडल वेव हो सिंगल फ्रीक्वेंसी तो उसमें दो साइड बैंड बनेंगे, और अगर हमारे पास रैंडम सिग्नल हो, कॉम्प्लेक्स वेव फॉर्म हो, तो उसमें नंबर ऑफ साइड बैंड्स बनेंगे यानी रेंज ऑफ साइड बैंड्स बनेंगे। द अपर साइड बैंड एंड द लोअर साइड बैंड कैलकुलेशन आर एज फॉलोज। अपर साइड बैंड इज इक्वल टू FC प्लस FM and lower side band frequency is equal to FC minus FM. This equation is for the upper side band and this equation is for the lower side band frequency. Okay. अच्छा, इस फिगर में आप देखें, दिस इज द फिगर ऑफ एम्पलीट्यूड मॉड्यूलेशन वेव, and the first one, which is figure A, this is intelligence or modulating signal, or we can say that this signal, the first one is what? This first one is actually the message signal. Then the second wave, which is B, this is a lower side band, and then the third C is a carrier. The fourth one, the D, is upper side band, and then the last one is composite amplitude modulation waves। अगर हम इन सब का को कंबाइन करके जो लास्ट में हमारे पास रिजल्ट बनती है तो उसको हम कहते हैं दिस इज कॉल्ड एनवेलप। सो you can see that if we mix this all together and we are getting what? The envelope of amplitude modulation wave. These instantaneous amplitude are added to produce this sum. So this, when we combine all these two, we add all these 1 2 3 4 band of frequencies, then we are getting what? This kind of waveform. Here frequency domain representation of amplitude modulation. When we observe amplitude modulation on oscilloscope, then we will see only amplitude variation of the carrier with respect to time. A plot of signal amplitude versus frequency is referred to as frequency domain display. We will call it as frequency domain display. A spectrum analyzer is used to display the frequency domain as a signal. One is oscilloscope, the other one is spectrum analyzer. So spectrum analyzer पे हम frequency domain देख सकते हैं. Bandwidth is the difference between the upper and the lower sideband frequency. So bandwidth is equal to upper sideband frequency minus lower sideband frequency. So जिस तरह पहले स्लाइड्स में हमने देखा था कि upper sideband frequency हम किस तरह फाइंड करते हैं, which is equal to fc plus fm maximum, and then minus here, so minus, and then the value of lower sideband frequency is fc minus fm max. So if we rearrange it and calculate, so you can see that if max and if max, this is negative and negative will become plus, so this will be 2fm max. fc minus fc will cancel out with each other and we will be getting 2fm max. तो हमने किस तरह बैंडविड्थ को अचीव करना है मैथमेटिकली, तो इस फ्रीक्वेंसी जो है अपर साइड बैंड माइनस लोअर साइड बैंड फ्रीक्वेंसी से हम बैंडविड्थ को अचीव कर सकते हैं. अच्छा, अगेन this figure is showing the relationship between the time and frequency domain. You can see that we are having this the carrier frequency, this greenish color carrier frequency fc, and then this side we are having upper sideband which is fc plus fm, and on the other side we are having fc minus fm lower sideband frequency, and then this wave is what? This wave is the modulating our intelligent signal, our message signal. So if we are combining this with this and then with this and then with this, we are getting amplitude modulation, our time domain amplitude modulation wave. You will be getting this type of wave and we call it is what? Envelope. So this is another details, and you can see peak amplitude of the sine waves. This is 1 and then 2 and so on. This is amplitude frequency domain. So this is the waveform of sidebands and frequency domain. Frequency domain representation of amplitude modulation पे हम एक एग्जाम्पल करेंगे. इधर आप देखें एग्जाम्पल नंबर 1. For a conventional amplitude modulator with a carrier frequency of 100 kilohertz and the maximum modulating signal frequency of 5 kilohertz, then determine frequency limits for the upper and lower sidebands. Then calculate, determine bandwidth. Then calculate upper and lower sideband frequencies produced when the modulating signal is a single frequency 3 kilohertz. Before it was 5 kilohertz, now it is 3 kilohertz. Draw the output frequency bandwidth. So we can do these applications, like for example, if frequency limits of the upper and lower sideband, so upper sideband frequency is equal to fc plus fm and lower sideband frequency is fc minus fm. Bandwidth is, as you can see in the above slides, bandwidth is f upper sideband minus lower sideband, and we can calculate it directly from this equation, which is 2f max fm max. So we can calculate the bandwidth from this formula. And similarly, the upper and lower side frequency produced when the modulating signal is, so if we are changing the modulating signal, f means fm is equal to 3 kilohertz. So if we change fm from 5 kilohertz to 3 kilohertz, then of course the upper side band frequency and then the lower side band frequencies will be changing. You can draw all these frequencies on the graph paper also. So students, you need to do it. This I can put here that this is your home assignment. So you have to do it and then submit it before 18th of July. Okay, example number 2. Suppose that we max value read from the graticule on oscilloscope screen is 4.6 division and we min is 0.7 division. Calculate the modulation index and percentage of modulation. So you can check the previous slides, the previous lectures of the previous lecture number 2. You can do this also. So again, this will be your practice example. If you have any question, then you can ask me. If you have any question, then you can ask me, or you have any problems, then you can ask me accordingly. Okay, now example number 3 for the AM waveform shown in figure. Determine peak amplitude of the upper and lower sideband frequency, peak amplitude of the unmodulated carrier, peak change in the amplitude of the envelope, modulation index, and percentage of modulation. So we also did this previously. This is the waveform for example number 3. See, every values is given. Try this yourself. If you have any question again, then I can help you out. So it's not difficult at all. You already have all the mathematical formula and the calculations and the explanation in your last lecture number 2. So again, this is your home assignment. Okay. So the mathematical representation and analysis of amplitude modulation. Representing both the modulating signal VMT and the carrier signal VCT in the trigonometric function, the AM double sideband full carrier modulator must be able to produce mathematical multiplication of these two analog signals. You can see we are having what? We are having VMT is Vm sine 2 pi FMT, and the carrier signal is Vc sine 2 pi FCT. If we combine this two, we multiply this two, so the AM modulator signal will be Vc plus Vm sine 2 pi FMT sine 2 pi FCT. We are getting equations like this. So when we are combining this with this modulator, we are getting this signal. Substituting Vm is equal to MVC gives, like we are putting the values of Vm is equal to MVC, because M is equal to Vm. You remember that M is equal to we remember that M is equal to what? Let me write it here. If you remember that M is equal to Vm divided by Vc. So if we rearrange it, Vm will be equal to, if we convert it here, then it will be, we will be getting Vm is equal to MVC. So Vm is equal to Vc, and then MVC sine 2 pi FMT sine 2 pi FCT. So if we are getting this Vc common from these two, like this one and this one, so Vc we put it here common, so 1 plus M sine 2 pi FMT, and then we're getting Vc is common, sine 2 pi FCT. So sine 2 pi FCT is this one. What is this? This is constant plus modulating signal, this all together, and this one is what? Unmodulated carrier. So we are getting the modulating signal separately and then the unmodulated carrier separately. Okay, let's see. The constant in the first term produces the carrier frequency while the sinusoidal component in the first term produces sideband frequencies. So VC sine 2 pi fct plus MVC sine 2 pi fmt and then sine 2 pi fct. So we are getting VC sine 2 pi fct minus MVC by 2 cos 2 pi fc plus fm into t. The first one is a carrier frequency and then the second is upper side frequencies, plus MVC divided by 2 cos 2 pi fc minus fm into t. This is the lower side frequency. So you can see that when we modulate a signal, we are getting three components. One is what? One is carrier frequency, the second one is upper sideband frequency, and then the lower sideband frequency. So this is mathematically, if you know the trigonometry, then you can see that we can convert this mathematical or this trigonometric equations into this form, and then from the trigonometry, of course you need to know about the trigonometry, like 2 sine theta cos theta. How can we convert it to some other good form according to our desired result? So we are getting these three components of frequencies. From the equation, it is very obvious that the amplitude of the carriers is unaffected by the modulation process. It means that from the modulation process, the carrier amplitude is unaffected. It has no effect on the carrier signal, but the amplitude of the side frequency depends on both the carrier amplitude and modulation index. Both depends on what? The amplitude of the side frequencies depends both on the carrier amplitude and the modulation index. 100% modulation, the amplitude of side frequencies are each equal to 1/2 the amplitude of the carrier. So this we are getting these conditions that if we are doing 100% modulation, so the side frequency must be what? Equal to 1/2 of the amplitude of the carrier signal. Generation of amplitude modulation double sideband with full carrier. Double sideband FC means full carrier envelope, showing the time domain of the modulated wave, carrier and sideband frequency. So you can see here the first one is upper sideband frequency, then the second one is carrier, the third one is lower side frequency, and then the last one we are getting what? The envelope. We are getting the envelope. If we combine the A, B and C, we are getting number D, which is what? Amplitude modulating signal. This is in the modulated signal. The last one is modulated signal. Okay. Now voltage spectrum for an amplitude modulator double sideband full carrier wave. You can see here, so the upper side frequency is also MEC divided by 2, the lower side frequency is MEC divided by 2, and the carrier frequency is at FC is EC. So this is the spectrum of the frequency spectrum of amplitude modulation with full carrier. So you can see we are having this carrier also. We are having carrier and sideband frequency. This type of spectrum we call it is amplitude modulator double sideband. It means double sideband means this side also have frequency, this side also have frequency. With full carrier means the carrier also is existing. So this kind of a wave is called DSBFC. Example: one input to a conventional amplitude modulator is a 500 kHz carrier with an amplitude of 20 V peak. The second input is the 10 kHz modulating signal. Okay, so you can see here 500 kHz is the carrier with an amplitude of 20 Vp. The second input is 10 kHz modulating signal. So you can see one is carrier, the other one is a message signal. So if we combine these two together, so is of sufficient amplitude to cause a change in the output wave of plus minus 7.5 V peak. Determine the upper and lower side frequencies, modulation index and percentage of modulation, peak amplitude of the modulated carrier in the upper and lower side frequencies, maximum and minimum amplitude of the envelope, expression for the modulated wave. So again, I'll request you all to try this example also. All the formulas for all A, B, C, D, E is given in the above slides. So again, try yourself. If you got any issue, then you can contact me. Okay, so try yourself. Okay, then the next slide, pulse modulation. Pulse modulation, when complex signals such as pulses or rectangular waves modulate a carrier or a broad spectrum of side band is produced. A modulating square wave will produce side bands based on the fundamental sine wave as well as the third, fifth, seventh, etc. harmonics. Amplitude modulation by square wave or rectangular pulses is referred to as amplitude shift keying. Amplitude shift keying is used in some types of data communication. This one, amplitude shift keying, we will cover in the digital modulation also a little bit, but pulse modulation, when we are having a rectangular wave or a triangular wave, so we can say that we will be getting not only the two side frequency but multiple harmonics frequency, and that type of modulation will be pulse modulation. You can see here the example of a pulse modulation by a square wave. So you can see that we are having the carrier in the middle, then the fundamental frequency one side and second side, then the third harmonic, fifth harmonic, seventh harmonic, okay, and then the other side also we are having the fundamental frequency, and then the second and the fifth, fourth and the sixth harmonics frequency on the other side. So side bands produced by the fundamental and its harmonic. So this is example. Okay, next slide, sideband and the frequency again. So modulating signal, this is actually the message signal. This one is the carrier, so you can see the carrier, and then the B100% modulation. You can see here when we are having the modulating signal is 0-1 form. So you can see that amplitude modulation of a sine wave carrier by a pulse or rectangular wave is called amplitude shift keying. Okay, when we are getting 0 here, you can see that the carrier signal frequency and the amplitude is less, and you can see at the output we are getting what 0. So you can see when we are getting 1, then the complete signal is modulated and we are getting the complete waveform here. But once we are getting 0, then we are having here 0, and then again we are getting the original signal back. So the part A is what? Part A, we are getting what? 5th% modulation. If this is 5th% modulation, and the last one is 100% modulation. This is 5th% modulation, and then the blue color is 100% modulation. Okay, continuous wave transmission can be achieved by turning the carrier off and on, as in Morse code transmission. Then continuous wave transmission is sometimes referred to as what? On-off keying, OOK, on-off keying. Splitter or splitter is term used to describe harmonic sideband interference. You can check these on-off keying and then continuous wave pulse modulation more. You can Google it also. If you have any issue, you can contact me. Okay, so we will finish our lecture until here. In the next lecture we will continue the rest of the topics inshallah. Thank you so much.